Okay, so ready to dive deep into something pretty mind-bending today. We're talking about the master algorithm.
Oh, yeah. This one's a big one. It's a concept that's been kind of floating around the fringes of computer science and AI research for a while now.
It's like one of those ideas that sounds like pure science fiction, but then you start to think about the possibilities, and it gets really, really interesting.
Exactly. And that's what makes it so fascinating to explore. So what exactly is this master algorithm anyway? Well, in the simplest terms, it's this hypothetical algorithm.
Hypothetical, right. Like, we don't actually know if it's possible to create.
Right, exactly. It's still very much in the realm of theory, but that's part of the fun. It's this idea that there could be a single algorithm, a universal learner, that's capable of extracting knowledge from any data you throw at it.
So not just like an algorithm that's good at playing chess or predicting the stock market. We're talking about an algorithm that could learn anything.
Exactly anything. And that's what sets it apart from the AI we see today, which is mostly specialized AI. You have algorithms that are great at recognizing faces or translating languages, but they're kind of one-trick ponies.
Right. So like the algorithm that recommends videos on YouTube probably wouldn't be very good at diagnosing diseases or composing music.
Exactly. But the master algorithm, the idea is that it wouldn't be limited to any specific domain or task. It could learn and adapt to anything.
Okay, so let's say just for fun that we could actually create this master algorithm. What are the implications? Like, what could we actually do with it?
Well, the possibilities are pretty mind-blowing. I mean, think about it. We're talking about an algorithm that could potentially automate the process of discovery and creation.
So it's not just about making our current technology better or faster. It's about creating entirely new things that we haven't even thought of yet.
Exactly. That's the really exciting part. It's like having a machine that could invent everything else. We could effectively automate the process of scientific discovery, of technological innovation, of artistic creation.
Whoa, hold on a second. Automate scientific discovery. Like, how would that even work?
Well, imagine an algorithm that could sift through all the scientific literature, all the data from experiments and observations, and find patterns and connections that humans might miss.
So instead of scientists spending years poring over journals and running experiments, you could have an AI that could do it in a fraction of the time.
Exactly. And not only faster, but potentially more accurately, too, because it wouldn't be limited by the same biases and assumptions that humans have.
Okay, I'm starting to see where this is going. So we're talking about accelerating scientific progress, potentially curing diseases, developing new technologies, maybe even solving problems like climate change.
Exactly. And that's just scratching the surface. I mean, think about the impact on other fields like education, finance, art, even something like cooking.
Whoa. Back up a second. Cooking. How could the master algorithm revolutionize cooking?
Well, imagine an algorithm that could analyze thousands of recipes and identify the underlying principles of flavor combinations and cooking techniques.
So it could create entirely new recipes that are guaranteed to be delicious.
Exactly. Or it could help you personalize your cooking based on your dietary restrictions or taste preferences.
Okay, now my mind is officially blown. So we're talking about not just automating tasks, but actually augmenting human creativity and ingenuity.
Exactly. And that's what makes the master algorithm so different from other forms of AI. It's not just about making machines that can do what we do, but making machines that can help us do things we never even thought possible.
This is pretty heavy stuff. But before we get too carried away, I think it's important to acknowledge that there are some pretty big challenges to overcome before we can even start talking about building this master algorithm.
Oh, absolutely. I mean, the idea itself is still very much theoretical. There are huge technical and philosophical hurdles to overcome.
Like, for example, one of the first things that pops into my mind is the sheer amount of data out there. I mean, even with all the information we have stored digitally, isn't that still just a tiny fraction of all the possible data points in the universe?
That's a great point. And that brings us to one of the biggest challenges in AI research, which is the problem of generalization.
Generalization. What do you mean by that?
It's not enough for an algorithm to just memorize data. It needs to be able to extract patterns from that data and then apply those patterns to new situations that it's never seen before.
So it's like learning to drive. You might practice in a parking lot, but to be a good driver, you need to be able to take those skills and apply them to real-world traffic with all its unpredictable chaos.
Exactly. And the same principle applies to AI. If we want to create an algorithm that can learn anything, it can't just be good at recognizing patterns in the data it's been trained on. It needs to be able to generalize those patterns to completely new and unforeseen situations.
That makes sense. So it's not just about the quantity of data, but also the quality and diversity of that data.
Exactly. And that's one of the biggest challenges we face in AI research today, because the real world is messy and complex and full of surprises, and our current AI systems are still pretty bad at dealing with that kind of complexity.
So how do we even begin to tackle this problem? Is there a blueprint for building this master algorithm?
Well, that's where things get really interesting, because there isn't one single approach. In fact, there are 5 major schools of thought in machine learning, each with its own unique perspective on how to build a universal learner.
5 schools of thought, like 5 different tribes, each with its own secret recipe for creating artificial intelligence.
Aha! That's a great way to put it.
Yeah.
Think of it like 5 different paths up the same mountain, each with its own set of challenges and rewards.
Okay, I'm intrigued. Let's meet these tribes, shall we?
Absolutely. Let's start with the symbolists. They're kind of the old guard of AI research. They believe that intelligence is fundamentally about manipulating symbols and logic.
So they're like the logicians of the AI world.
Exactly. They see learning as a process of inverse deduction, kind of like a detective solving a case. They use logic and rules to build a model of the world, and then they use that model to make predictions and solve problems.
So instead of just crunching numbers, they're looking for those logical connections, those if this then that relationships that underpin our understanding of the world.
Precisely. And they've actually had some pretty impressive successes using this approach, especially in areas like expert systems and knowledge representation.
Expert systems, what are those?
They're basically computer programs that try to emulate the decision-making abilities of a human expert in a particular field. Like, for example, there are expert systems that can diagnose diseases or troubleshoot technical problems.
So it's like having a doctor or an engineer in a box.
Kind of. But the key is that these systems are built on a foundation of logic and rules. So they're very good at reasoning through problems step by step and coming up with solutions that are consistent with their knowledge base.
Okay, that makes sense. But wouldn't a purely rule-based approach struggle with the messiness and unpredictability of the real world? I mean, not everything follows neat logical rules, right?
That's a great point, and that's one of the key limitations of the symbolist approach. While logic is a powerful tool, it can sometimes struggle to capture the nuances and uncertainties of the real world.
Right, because sometimes things just happen and there's not always a clear logical explanation.
Exactly. And that's where some of the other tribes come in. They offer different perspectives on how to deal with the complexity and ambiguity of the real world.
Okay, so if the symbolists are the logicians, who are the next contenders in this quest for the master algorithm.
Next up are the connectionists. And they take their inspiration from a completely different source, the human brain.
So instead of trying to create a perfectly logical machine, they're trying to replicate the messy, complex, and frankly, quite amazing way that our own brains learn.
Precisely. Connectionists build learning machines using artificial neural networks, which are complex structures of interconnected nodes that mimic the way neurons in our brains communicate and process information.
So they're basically trying to build a digital brain. But how do they even begin to replicate something as complex as the human brain? I mean, we barely understand how our own brains work.
It's a formidable challenge, for sure, but connectionists have made significant progress by focusing on the functional aspects of the brain, particularly how it learns from experience.
So instead of getting bogged down in the biological details, they're looking at the big picture of how the brain processes information and adapts to new situations.
Exactly. One of their key algorithms is called backpropagation. Think of it as a feedback mechanism that allows the network to learn by adjusting the strength of connections between those nodes based on the results it gets.
Okay, so it's like the network is constantly fine-tuning itself, getting better at a task with each attempt.
Precisely. And this approach has been incredibly successful in recent years, especially in areas like image recognition, natural language processing, and machine translation.
Right. I've heard a lot about deep learning, which I think is based on neural networks.
Yeah, exactly. Deep learning is basically a subset of connectionism. It involves training very large and complex neural networks on massive amounts of data.
And that's how we're getting those amazing results with things like self-driving cars and facial recognition software.
Precisely.
Yeah.
But the question is, can this approach really lead us to the master algorithm? Is just copying the structure and basic functions of the brain enough to achieve true artificial intelligence?
Right. I mean, our brains do so much more than just process information. We feel emotions, we have consciousness, we're creative.
Exactly. And that's the debate that rages on within the connectionist camp. Some believe that by faithfully replicating the brain's structure and functions, we'll eventually unlock the secrets of consciousness and general intelligence. Others argue that we need to go beyond mere mimicry and develop new algorithms and architectures that capture the essence of human thought, creativity, and even emotions.
That's a lot to unpack. So we've got the logicians and the brain builders. Who else is vying for the title of master algorithm champion?
Well, if the connectionists take their cues from biology, the next tribe, the evolutionaries, they draw their inspiration from the grand process of evolution itself.
So instead of like trying to design a perfect learner from scratch,
Yeah.
they're saying, let's just let the algorithms evolve and adapt survival of the fittest, just like in nature.
Exactly. Evolutionary algorithms work by generating a population of potential solutions and then testing them against a given problem. And then the ones that perform the best, they get to breed and create the next generation. And over time, this process can lead to some pretty remarkable results.
So it's like breeding a racehorse or a prize-winning dog. You start with a bunch of candidates, and then you selectively breed the ones with the most desirable traits.
Yeah, that's a good analogy. But instead of physical traits, we're talking about algorithmic traits, things like accuracy, efficiency, and robustness.
Okay, so let's say you want to create an algorithm that can predict the stock market. You could start with a bunch of different algorithms, each with its own set of parameters, and then you could let them compete against each other in a simulated market environment.
Right. And the algorithms that make the most money, they get to reproduce and pass on their winning strategies to the next generation.
And over time, the system would evolve more and more sophisticated algorithms
Yeah.
that are better and better at predicting the market.
Exactly. But the really cool thing about evolutionary algorithms is that they can be applied to a wide range of problems, not just financial ones.
So like, what else could we use them for?
Well, pretty much anything that involves optimization or problem solving. You could use them to design new drugs, optimize traffic flow control, robots, create art, even compose music.
Whoa. Back up a second. Create art. Compose music. Are you saying that algorithms can be creative?
Well, that's a whole other can of worms. But yeah, there are actually algorithms out there that can generate some pretty impressive creative output.
Like what kind of stuff?
Well, there's this program called AIVA that composes classical music. It's actually been used to score films and even write a whole symphony.
No way. That's incredible. But how's it work? Does it just like randomly combine notes until it sounds good?
Not exactly. It's actually trained on a massive data set of classical music, and it uses that data to learn the rules of harmony, melody, and rhythm.
So it's like it's absorbing the essence of classical music and then using that knowledge to create something new.
Exactly. And the results are pretty amazing. I mean, you can definitely tell that it's composed by an AI, but it's still beautiful and moving music.
Wow. Okay. My mind is officially blown. So we've got algorithms that can predict the stock market, design drugs, and compose music. What's next? Are they going to start writing poetry and painting masterpieces?
Well, who knows? But that's the beauty of evolutionary algorithms. They're constantly evolving and surprising us. But there is one potential drawback to this approach, and it's something that we touched on earlier.
What's that?
Well, evolution is a notoriously slow process. I mean, it took billions of years for life on Earth to evolve from single-celled organisms to the complex ecosystems we see today.
Right. So wouldn't that make this approach impractical for solving real-world problems? I mean, who has billions of years to wait around for an algorithm to evolve?
That's a valid point. But luckily, we don't have to wait that long because we can simulate evolution at an accelerated pace using computers.
So it's like fast-forwarding evolution, compressing billions of years into a few hours or days of computation.
Exactly. And that's what makes evolutionary algorithms so powerful. We can run millions or even billions of generations in a relatively short amount of time, allowing us to explore a vast space of potential solutions and discover optimal strategies much faster than nature ever could.
That's pretty mind-boggling. So we can basically hack evolution to create algorithms that are specifically tailored to solve our problem.
Exactly. And that's why I think evolutionary algorithms have so much potential, because they offer a way to create intelligent systems that are not only effective, but also adaptable and robust.
Okay, so we've got the logicians, the brain builders, and the evolution hackers. Who else is in the running for the master algorithm?
Well, next up are the Bayesians, and they bring a whole new perspective to the table. They approach learning from a probabilistic perspective.
Probabilistic, what do you mean by that?
Well, they see the world as a web of probabilities where everything is uncertain and our knowledge is constantly being updated based on new evidence.
So instead of searching for absolute truths, they're trying to quantify uncertainty and make the best possible decisions based on the information they have.
Exactly. Bayesian learning algorithms work by starting with a prior belief about the world, and then they update that belief as they encounter new data.
So it's like starting with a hypothesis and then refining that hypothesis as you gather more evidence.
Exactly. And the beauty of this approach is that it allows algorithms to learn from their mistakes and adapt to changing conditions.
So it's like a continuous learning cycle where the algorithm is always refining its understanding of the world.
Precisely. And this approach has been very successful in a wide range of applications, from spam filtering to medical diagnosis.
Okay, so let's say you're building a spam filter. A Bayesian algorithm could start with a general assumption about what spam looks like, and then it would constantly refine that assumption based on the emails you mark as spam or not spam.
Exactly. And over time, it would become incredibly accurate at distinguishing between legitimate emails and junk mail. But Bayesian learning goes far beyond spam filters. It can be applied to all sorts of problems where there's uncertainty and a need to make decisions based on incomplete information.
So like what else could we use it for?
Well, for example, in medical diagnosis, a Bayesian algorithm could be used to calculate the probability that a patient has a particular disease based on their symptoms, medical history, and test results.
So it's like a doctor, but instead of relying on intuition and experience, it's using cold, hard data and statistics.
Exactly. And because it's based on probabilities, it can also quantify the level of uncertainty in its diagnosis. So it might say something like, there's a 90% chance that the patient has this disease.
That's actually pretty helpful because it gives you a sense of how confident the algorithm is in its prediction.
Exactly. And that can be really valuable in making decisions about treatment or further testing.
Okay, so Bayesian learning sounds pretty powerful. But are there any limitations to this approach?
Well, like any approach, it has its strengths and weaknesses. One of the main challenges is that it can be computationally expensive, especially when dealing with large data sets.
Right, because you're basically calculating probabilities for every possible outcome, which can get pretty complicated.
Exactly. Another challenge is that Bayesian learning requires a prior belief, which can be subjective and difficult to determine.
So it's like you need to have some initial assumptions about the world before you can even start learning.
Precisely. And if those assumptions are wrong, it can lead the algorithm astray.
Okay, so it's not a foolproof system.
Yeah.
But it definitely seems like a promising approach for dealing with uncertainty and making decisions in complex situations.
Absolutely. And it's one of the most widely used approaches in machine learning today.
Okay, so we've got the logicians, the brain builders, the evolution hackers, and the probability masters. Who's our final contender in this quest for the master algorithm?
Our last tried is the analogizers, and they bring a very different perspective to the table. They believe that the key to learning lies in finding similarities between things.
So it's like understanding that the structure of an atom is analogous to the structure of the solar system, or that the flow of traffic is similar to the flow of electrons in a circuit.
Exactly. They argue that we humans learn by drawing analogies, by recognizing patterns and relationships between seemingly disparate concepts, and they're trying to develop algorithms that can do the same thing.
So it's like finding those hidden connections, those aha moments where you suddenly see how two seemingly unrelated things are actually deeply connected.
Precisely. And they believe that this ability to draw analogies is fundamental to human cognition, and that it's the key to unlocking true artificial intelligence.
Okay, I can see how that could be powerful. But can analogy really be the basis for a universal learner? I mean, isn't it a bit too fuzzy? Like, how do you even begin to formalize analogy into an algorithm?
That's a common criticism of the analogizer approach. Some argue that analogy is too subjective, too dependent on human interpretation to be formalized into a robust learning algorithm.
Right, because what seems like a clear analogy to one person might seem completely nonsensical to another.
Exactly, but analogizers counter that our entire understanding of the world is built upon analogies, that we constantly use metaphors and comparisons to make sense of new experiences and ideas.
So they're saying that analogy isn't just a literary device, it's a fundamental cognitive process.
Exactly, and they believe that if we can crack the code of how analogy works, we might be able to build machines that can learn and think in a truly human-like way.
Okay, so now we've met all 5 of our tribes, each with its own unique approach to building the master algorithm. But is the quest for a universal learner really about choosing one tribe over the others? Or is there a way to combine their strengths and create something truly groundbreaking?
That's the big question, isn't it? Can these different approaches work together?
Yeah.
Or are we looking at like a battle royale of AI philosophies?
Right, because on the one hand, you have the symbolists, all about logic and rules.
Yeah.
And then you have the connectionists trying to rebuild the brain. And then you have the evolutionaries just letting the algorithms run wild. And then the Bayesians with their probabilities. And then the analogizers looking for hidden connections. It's a lot to wrap your head around.
It is. It's like a scientific Tower of Babel.
Yeah.
But
yeah.
I think that's what makes this quest so exciting, because it's not just about finding the right algorithm. It's about understanding the nature of intelligence itself.
So maybe the master algorithm isn't a single algorithm. Maybe it's like a combination of all these different approaches working together.
Exactly. Maybe it's not a winner-take-all situation. Maybe the real breakthrough lies in finding ways to integrate these different approaches, to create a hybrid learner that leverages the strengths of each tribe.
So like a kind of AI Voltron.
Uh-huh. Yeah, something like that. And there are already researchers exploring these kinds of hybrid approaches. For example, there's something called ensemble learning, where you combine multiple algorithms to make predictions.
So it's like having a team of experts, each with their own area expertise working together to solve a problem.
Exactly. And the results can be really impressive because each algorithm can compensate for the weaknesses of the others.
Okay, that makes sense. But let's step back for a second and talk about the so what of all this. Why should we even care about this master algorithm? What's in it for us?
Well, I think the potential benefits are enormous. I mean, just think about the impact it could have on science.
Okay, so we've talked about accelerating scientific discovery, curing diseases, developing new technologies, all that good stuff. But are there any potential downsides? Any risks we should be aware of?
Of course.
Yeah.
As with any powerful technology, there are always risks. And I think it's important to be aware of those risks and to have open and honest conversations about them.
So like, what are some of the things we should be thinking about?
Well, for one thing, we need to make sure that these algorithms are designed and used ethically. We don't want to create systems that are biased or discriminatory or that could be used for harmful purposes.
Right. Because if these algorithms are going to be making decisions that affect our lives, we need to make sure that they're making fair and just decisions.
Exactly. And we also need to think about the economic implications. If these algorithms can automate many of the jobs that humans currently do, what will happen to those workers? Will they be displaced? Or will new jobs be created?
Yeah, that's a big question, and one that I don't think anyone has a clear answer to yet.
Right. And there are also philosophical questions to consider. What does it mean to be human in a world where machines can learn and think like we do? What are the implications for our sense of identity and purpose?
Okay, now we're getting into some deep existential territory. But I think it's important to have these conversations because the future of AI isn't just a technological issue. It's a societal issue. It's about who we are and what kind of world we want to create.
Exactly. And I think the quest for the master algorithm is forcing us to confront these questions head on. It's a journey of discovery, not just about the nature of intelligence, but also about the nature of humanity.
Well said. Well, it looks like we've reached the end of our deep dive into the master algorithm. It's been a fascinating journey full of mind-bending concepts and thought-provoking questions.
It has. And I think we've only just scratched the surface. There's so much more to explore and discover in this field.
Absolutely. And I'm sure we'll be revisiting this topic again in the future. But for now, thanks for joining us on this deep dive into the master algorithm.
It's been a pleasure.
And don't forget to like, share, and subscribe to The Deep Dive for more explorations into the fascinating world of knowledge and discovery.